I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss some definitions and terminology involved with the chapter or the module Semiconductor Devices in the course Applied Physics. So, before starting discussing the definitions and terminology, let us first look at what a definition means or what a terminology is. So, let us see first what a definition is. The act of defining or of making something definite, distinct or clear. That is what we call a definition. Or it is the formal statement of the meaning or the significance of a word or a phrase or an idiom as it is found in the dictionaries. Or it is a statement expressing the essential nature of something. That is what we call a definition. Now, why is a definition so important? Why you will have to define things? Because definitions enable us to have a common understanding of a word or a subject. If it is defined in a proper manner, all those who are using the same definition will be at the same platform. So they allow all of us to be on the same page when discussing or reading about an issue. Therefore, we need to make sure that properly define our words and phrases so that all will understand. Now coming to terminology. What is terminology? It is the body of terms used with a particular technical application in a subject of study or a profession. Now, what is the importance of terminology? It plays a very important role in understanding the context or specialized texts. So, whenever we are talking in a particular context, so these terminology plays a very important role. Then understanding the intricate terminological details of the technical and scientific context helps students comprehend what the main message of the content or the subject is. Not only that, it also helps specialists to transmit the content in a very effective manner. So with this, we are going to start with the discussion of definitions and terminology involved in Module 3 of the course Applied Physics, and the name of the module is Semiconductor Devices. So let us see the brief outline. What we have here: direct and indirect band gaps. Then we have a PN junction, VI characteristics, energy band diagram, then biasing of a junction, construction and working of LED, photodetectors, pin or avalanche photodiode, and finally the solar cell. So we are going to discuss all the definitions and terminology that is involved with all these topics. So now the first one. What do you remember by generation of an electron-hole pair? So we have to explain what is the generation of electron-hole pair. So carrier generation is a process where electron-hole pairs are created by the excitation of an electron from the valence band of the semiconductor to the conduction band, thereby creating a hole in the valence band. So what we are trying to understand is how these electron-hole pairs are generated. So for that, first we will try to understand what a valence band is, then what is a conduction band, and how is the energy gap in a semiconductor, and then we will see the process. So these are the key terms here. So let us see the energy band diagram. for a semiconductor. So if we are talking about a semiconductor, if we are plotting energy band diagram, this denotes the energy levels. Now, valence band means it is the range of energies possessed by all the valence electrons. So, if I am showing them by means of levels, all these levels put together form a band which we call as valence band. So, now suppose this is the valence band. What is valence band? It consists of all the range of energies possessed by valence electrons. Then we also have a conduction band. So conduction band represents the range of energies possessed by conduction electrons. What are conduction electrons? They are free electrons which are ready to conduct or which help in conduction. So if I denote the conduction band, so in a semiconductor, there is a small energy gap. There is an energy gap of the order of 1 electron volt because we are talking about a semiconductor. Now, if there is a gap between the valence band and the conduction band, and if you see, generally a semiconductor, if it is taken at 0 Kelvin, it behaves as an insulator. Means all the valence electrons are held tightly to the nucleus or to the atom. The electrons are here in the valence band. The valence band is full, but the conduction band is empty. Now, if we can supply some energy, to these electrons, so the minimum energy should be at least 1 electron volts to overcome this band gap. Then this electron may move to the conduction band. So depending upon how many electrons are moving from the valence band to the conduction band, there are holes that are generated in the valence band. Suppose this electron has gone here. So in the place of this electron here, we will have a hole. There is a hole here because this electron has gone to the conduction band. So now whenever an electron is moving from the valence band to the conduction band, there is a hole that is generated here in the valence band. So what we are seeing here, carrier generation is a process where electron-hole pairs are generated by exciting of electron from the valence band to the conduction band. So here we are using the temperature. We are increasing the temperature for excitation of electrons from the valence band to the conduction band. So what is happening? Creating a hole in the valence band. So whenever an electron moves from the valence band to the conduction band, a hole is generated here. So this is how the whole electron-hole pairs are generated. Now what is a diode? A semiconductor device with 2 terminals, typically allowing the flow of current in one direction only. Diode. Di means 2, ode means electrodes. So they will have 2 electrodes. We will call them as 2 terminals. So the best example we have is a PN junction diode. P and N. So we will have 2 terminals, one on this side and one on the other side. So there are 2 terminals, typically allowing the flow of current in one direction only. Suppose we do the forward bias, then you have the flow of electrons from N type to the P type. So the flow of current is only in one direction. Now explain the meaning of a recombination of an electron-hole pair. So we have just now seen the generation, the carrier generation or the generation of an electron-hole pair. Now what is recombination? Recombination of an electron-hole pair. So recombination is the reverse process of generation. It is the reverse process where electrons and holes from the conduction band and valence band respectively, means we have the electrons in the conduction band and holes in the valence band. They will recombine and are annihilated. Annihilated here means generation of energy, conversion of that into energy. We are calling it as annihilation. So it is a reverse process of generation. So in recombination, what is happening? The electrons from the conduction band are combining with the holes in the valence band, and there is generation of or emission of energy, maybe in the form of photons. Now, what is a photodiode? Photodiode. So, a photodiode is a semiconductor device. Diode we are talking about, it's a semiconductor device that converts light into electric current. So, what we see here is in a photodiode, always we see the conversion of light energy into electrical energy. So what is the principle here? Conversion of light energy into electrical energy. So the current is generated when photons are absorbed in the photodiode. So if you have a photodiode and when light falls on this photodiode at the junction, the light is absorbed. Light is falling in the form of photons. So, I say photons are absorbed and current is generated. So, it gives rise to current. So, that is what we call a photodiode. Now, define LED. What is an LED? So, the full form is light-emitting diode. So, the name itself says it is emitting light emitting diode. It is a semiconductor device that emits visible light which is in the visible spectra when an electric current passes through it, So, I can say the principle here is conversion of electrical energy into light energy. So what is the phenomenon we are seeing here? When current passes through it, it emits light, visible light, means light is emitted in the visible region of the spectrum. So that is what we are calling an LED. So if you are asked to write the principle on which it works, it is the conversion of electrical energy to light energy. Next, what is a photo detector? Photo, the word photo is always related to light. So, a photo detector is a PN junction that converts light photons into current. So, a photo detector detects the light and it converts it into current. Again, it's a conversion of light energy to electrical energy. Now, what is photovoltaic effect? So, again, there are two terms, photovoltaic effect. So, it is a process that generates voltage or electric current. Voltage or current in a photovoltaic cell when it is exposed to sunlight. So, here photo is related to light. So, when this particular cell, photovoltaic cell, is exposed to light, it absorbs the energy and it generates a voltage which gives rise to current. So, it generates a voltage or electric current. Next, describe a solar cell. So, a solar cell or a photovoltaic cell is an electrical device that converts the energy of the light into electricity by the photovoltaic effect. So, in solar cell, what is the phenomenon that is occurring? Conversion of light energy into electrical energy, which is a physical and a chemical phenomenon. This conversion process is both physical as well as chemical. So we are calling that as a solar cell, a cell which converts the light into electrical energy by the photovoltaic effect. We call it as solar cell. Now, what is the meaning of biasing of a diode? What is biasing? Biasing of a diode means applying DC voltage across the terminals of a diode. So, what is biasing and why do we need biasing? We are going to understand here. What are the types also? So, biasing means applying DC voltage. How do we apply it? Now, suppose we take a diode. We will take a PN junction diode. So, I'll consider a PN junction diode. This is P, this is N. Means we take a semiconductor material and one side of it is doped with a P-type material, or we take N-type and one is doped with a trivalent impurity which gives rise to P-type. So we have PN and this is the junction, PN junction. So we call it a PN junction diode. Now this has two terminals. So in biasing, what we do is we apply a DC voltage to this PN junction diode. Means I will connect this to a DC supply. This is positive and this is negative. So whenever we are connecting this to a DC supply, and if it is connected in such a way, the P type is connected to the positive, we call it as forward bias. This is forward bias. We are doing the biasing of the diode by conducting the DC voltage across it. Since the P type is connected to the positive, we call it as forward bias. Now, what if we connect it in the reverse manner? Means, if the P type is connected to the negative terminal and the N type is connected to the positive terminal. So, P is connected to negative, N is connected to positive. So, when we are connecting it in such a manner, then we call it as reverse bias. This is reverse. So, there are two types of biasing. We are applying a DC voltage. It all depends on how we apply the voltage. If P is connected to positive, it is forward bias. And if P is connected to negative, it is reverse bias. Now, state Ohm's law. Ohm is the name of the scientist. So, it's a very famous law and very important and useful. So, what it states is, as long as the physical state of the conductor remains the same, the electric current is proportional to the voltage. So, here, whenever we are talking about Ohm's law, if you take a conductor whose length, the area of cross section and the temperature, that is what we mean by the physical state, remains the same, the electric current is proportional to the voltage. So, V is proportional to I. Or V upon I must be a constant. And this constant, we get it to be the resistance of the conductor. So, we can write it as V is equal to IR. This is the famous form of Ohm's law. Where from it comes is from our basic definition that the voltage is always directly proportional to the current. So, more the applied voltage, more the current. And it is a constant which depends upon the resistance in the circuit. So, V is equal to IR. Now, what are direct band gaps in semiconductors? What is a direct band gap? A semiconductor in which the bottom of the conduction band and the top of the valence band occur at the momentum K is equal to 0. So, we have already discussed about semiconductor and the band gap. Now what we are talking about is a direct band gap. The emphasis is here. What is direct band gap? So now it occurs at the momentum or the vector, same wave vector. So how do we represent it? Now if I draw the energy band diagram, we have, this is the energy band diagram, energy versus bands we show. Now if this is the conduction band, I will call this is the conduction band or EC. EC is the lowest level of the conduction band, bottom of the conduction band. And now when I talk about the valence band, this is the valence band. I call this as EV. This is the topmost of the valence band. So what we are understanding here, bottom of the conduction band. This is the bottom of the conduction band and the top of the valence band. So this is the top of the valence band. They occur at the same momentum. K is equal to 0. Then we say it is a direct band gap. Energy is released in the form of radiation during band-to-band electron recombination with the hole, and we call it as direct band gap semiconductor. So when this process is there, the electron can very easily recombine with the hole in the valence band. So whenever there is a recombination, energy is emitted, that is a photon is emitted. So we are calling it as energy is released in the form of radiation or photons. So this is what we call a direct band gap. Next, what is meant by threshold voltage? Threshold. Threshold is a general term actually. If you see, when we are talking about threshold voltage for a particular device, we can refer to that. So threshold voltage refers to the voltage at which certain result occurs. What happens at that particular voltage? We call it as threshold voltage. Usually it is the minimum voltage required for conduction to occur. What is the minimum voltage that we have to apply so that it starts conducting? That is called the threshold voltage. Now, what is the biasing in a light emitting diode? We have seen what a light emitting diode is. We call it as LED. It works on the principle of conversion of electrical energy to light energy. So we are saying light is emitted. So light emitting diode is connected in forward biasing to produce light. So the symbol we use for light emitting diode is this, the symbol. You should know the symbol also. This is the symbol for a diode, PN junction diode. But because it is LED, it emits light, this will be the symbol. So the light emitting diode is connected in forward bias. We have already discussed what a forward bias is. Forward bias means this is connected to the positive and this is connected to the negative. Whenever we see this symbol, this side is plus positive P and this is N negative. So the positive is connected to the positive and the negative is connected to the negative. Then you say it is forward bias. So whenever we take an LED, we always connect it in forward bias. Now, what is the principle behind light emitting diode? How is it emitting light? What is the principle? So the electron from the N side recombines with the hole on the P side and light is emitted due to recombination. We have already discussed what is recombination. It is the reverse process of carrier generation where an electron will combine with the hole, and whenever this recombination occurs, energy is emitted in the form of radiation, which we call as photon. So light is emitted. So when is it emitted? When an electron from the N side, we have electrons on the N side. Now when we are talking about a PN junction diode, this is P and this is N. So when I say p-type, where we are adding a trivalent impurity, so it is an acceptor impurity where we will have all holes. It is excess of holes here. And when we say n-type, we are adding a pentavalent impurity. Pentavalent impurity means a donor impurity where there are excess of electrons. So there are more electrons here. So when an electron from the n side combines or recombines with the hole on a p side, energy is emitted. So we call it as recombination. So light is emitted and we call it as light emitting diode. Next, explain the term diffusion in a semiconductor. What is diffusion? So the flow of charge carriers from higher density to lower density is called diffusion. Diffusion means it is the flow of charge carriers. How do the charge carriers flow? Always from higher density to lower density. So again we take the example of the PN junction diode which we have seen just now. So in p-type, the majority carriers are the holes. These are the holes. And in n side, the majority carriers are the electrons. The crosses represent the electrons and the polar circles represent the holes. Now, the density of electrons is more on the n side, so they will move to the lower density side. So when we are connecting p to the positive and n to the negative, so these movement of electrons and holes. So I can also say that electrons are the majority carriers here and holes are the majority carriers here. So there is always a movement of charges from higher density to lower density and we call it as diffusion. Next, describe the recombination phenomena which we have already discussed. The combination of an electron from the conduction band to the valence band is called a recombination. We have already discussed. Next, what is the drift velocity of an electron? What is the velocity? How an electron is gaining that velocity? So the velocity gained by an electron when an electric field is applied is called the drift velocity. So whenever we apply an electric field, there exists a potential difference between the two terminals. So because of that, the electron will gain the velocity and we will call it as drift velocity. Then how many junctions do a diode consist of? Di means two electrodes. But how many junctions will be there in a diode? There will be only one junction which has one cathode and one anode. When I am talking about diode, two electrodes. What are the two electrodes? Cathode and anode. They are two electrodes. So when you have a diode with two electrodes, we have only one junction. The junction is of p-n type. No, we have seen. We are talking about two electrons, p, electrodes, p and n. And this is the only one junction that is formed. So, only one junction is there in a diode. Next comes, what are the applications of a junction diode? Diodes are used in clamping circuits. We are using them in clamping circuits for DC restoration, direct current restoration. Also, they are used in clipping circuits where we will have to clip the waves for wave shaping. Whenever wave shaping is required, so we need to clip. So, in the clipping circuits also we are using this junction diode. And in voltage multipliers, whenever the voltage has to be multiplied, we use the junction diodes. And also as a switch, it can be used as a switch in digital logic circuits for on and off positions, which is used in computers. So wherever we are using the digital logic circuits in computers, that will function as a switch. Now, which rectifier requires 4 diodes? Where are we seeing these 4 diodes? Which type of rectifier? So when a simple transformer without a center tapped secondary is used, 4 diodes are required. So in a transformer, we may need 4 diodes if we are not using a center tapping. Okay, instead of the one needed for half wave rectification. So what is half wave rectification? That also we will see and understand. Then 4 diodes arranged in this way are called as a diode bridge or bridge rectifier. So how these diodes are arranged? So this is one diode. This is another diode. So diode 1, diode 2, diode 3 and diode 4. So what is a rectifier? A rectifier is the one which converts AC to DC. So in half wave rectification, only one half of the wave, if you are talking about a wave like this, in half wave rectifier when we are using a single diode, only one half of the wave is being rectified. But in a simple transformer, what we are doing without center tapping, we are using 4 diodes that are connected in this manner. If you put a voltage across this, so you'll be able to understand. So this is the way they are arranged and you will call it as a bridge rectifier. Now, how does an ideal diode work? What is an ideal diode? An ideal diode is a diode that behaves like a perfect conductor when the voltage applied is in forward bias. So we have discussed forward bias means P connected to the positive and N type connected to the negative. So when it is connected in such a way in forward bias, it acts as a conductor. But when the voltage is applied in reverse bias, reverse means P is connected to the negative, N is connected to the positive. It behaves as a perfect insulator. So in forward bias, it acts as a conductor. It starts conducting. But when it is kept in reverse bias, it will act as a perfect insulator. So this is how an ideal diode works. So what happens here when positive voltage is applied across the anode to the diode conducts forward current instantly. So it allows the current to flow through, conductor means. So it conducts forward current. Now what happens if a diode is shorted? Shorted means we say bad diode or an open diode. It does not allow the current to flow in either direction, in any direction. It will not allow the current to flow. And a shorted diode will have the same voltage drop in both the directions. There is the same voltage drop, that is approximately around 0.4 volts in both the directions. Then you say it is shorted. Can a diode short circuit? So ideally a diode would act like a short circuit, that is 0 voltage across it, if it is conducting current. So in the conducting mode, it behaves like a short circuit. Now, how can you tell if a diode is blown or it's not working? A diode is reverse biased when the positive test lead is on the cathode and the negative test lead is on the anode, which we have already discussed. So reverse, when we are telling positive is on the cathode and the negative is on the anode, then it is reverse biased. Now this reverse biased resistance of a good diode displays OL. It shows as open line on a multimeter. If you see the display on the multimeter, what you see here, it is OL. Now if the diode is bad, the readings will be the same in both the directions. If it is bad, means if it is blown off, the readings are the same in both the directions. That is how we identify if the diode is blown. Now, what does a Schottky diode do? What is a Schottky diode? Schottky diodes are used for their low turn-on voltage, fast recovery time and low energy loss at higher frequencies. Actually, what is the difference between an ordinary diode and a Schottky diode? Here we are taking a semiconductor material and a metal which will form a junction. Then we call it as Schottky diode. So in Schottky diode, the turn-on voltage is very low, means it will turn on at a very low voltage, and there is a fast recovery time and low loss of energy at higher frequencies. So these characteristics make Schottky diodes capable of rectifying a current by facilitating a quick transition from the conducting to the blocking state. So when it is conducting, if it has to be blocked immediately, so we will use a Schottky diode. Now, what is the difference between a Zener diode and a Schottky diode? So, we have just seen that for a Schottky diode, the breakdown voltage is very high. The voltage at which it breaks down is very high. But for a Zener diode, the breakdown occurs at a relatively low reverse voltage. So, here the applied voltage is the reverse voltage, and the breakdown occurs at a very low reverse voltage. So that is the main difference between Schottky diode and Zener diode. Now, why is Zener diode is reverse biased? We have seen that it has a low cutoff voltage. Why is it reverse biased? Why are we conducting it in reverse bias? So a reverse bias Zener diode exhibits controlled breakdown. There will be controlled breakdown and allows the current to keep voltage across the Zener diode close to the Zener breakdown voltage. So it is acting as a regulator. There is a controlled breakdown and it allows the current to keep the voltage across the Zener diode very close to the Zener breakdown voltage. Now, what is Zener breakdown voltage? We are talking about Zener breakdown voltage. What is it? So, when a reverse voltage is applied to a Zener diode, it causes a very intense electric field to appear across a narrow depletion region. So, whenever we are talking about a Zener diode, it is highly doped. So, what happens here is the depletion layer will be very narrow. So, because the depletion layer is very narrow, there will be an intense electric field across the depletion region. So, that is what we call it as a Zener breakdown voltage. Then, why a Zener diode is highly doped? I said Zener diode is highly doped. Why is it highly doped? They are highly doped so that in the reverse bias, the junction potential is increased. And hence, the current through the diode increases rapidly. So, as the potential increases, the current also increases. Potential is nothing but we are changing the levels, very higher level and very lower level. So, there is rapid movement of current. So, that is why we are doping it very highly. So, by doping it high, the junction potential is increased and this in turn helps the current to pass through it very rapidly. Now, what happens if the Zener diode is forward bias? We said it is generally connected in reverse bias. But what happens if the Zener diode is forward biased? So when it is forward biased, it will simply act like a general purpose signal diode. So what a general purpose signal diode does, when it is in the forward bias, it starts conducting, and when it is in the reverse bias, it does not conduct. So that is how a Zener diode will behave if it is conducted in the forward bias. So when biased in the forward direction, it behaves just like a normal signal diode. Now, how Zener diode works as a voltage regulator? How are we using it as a voltage regulator? So, Zener diodes are widely used as voltage references and also as shunt regulators to regulate the voltage across small circuits. Wherever you have small circuits and you need to regulate the voltage, then we are using Zener diodes. So, what happens there? When connected in parallel with a variable voltage source, so that it is reverse biased, a Zener diode conducts when the voltage reaches the diode's reverse breakdown voltage. Shunt means what here? Suppose you have a circuit, a small circuit, where we have a current flowing through this. Now, when we are putting a Zener diode, this is the symbol of the Zener diode. This is called shunt across the load if you are putting it. Then what happens when connected in parallel with a variable voltage source, so that it is reverse biased. Reverse biased means we should have connected it positive to negative. And negative to positive. Then when the voltage reaches the Zener diode's breakdown voltage, only then it starts. Next, what are the advantages of Zener diode? So the ability of the Zener diode to control and reverse the part of the current flowing through it means it can be used to regulate and stabilize the voltage. So wherever there are excess voltages flowing, it will try to regulate and also stabilize the voltage. And because of that, it prevents the problems that can occur when the supply or the load voltage varies. Means whenever there are fluctuations in the voltage, generally we see even in our houses for domestic purposes, whatever voltage that is supplied, there may be fluctuations. So because of that, what we do is, if a Zener diode is used, it will regulate and stabilize the voltage. Thereby it prevents the problems of excessive load. Now, what are the limitations of Zener diode voltage regulator? It has low efficiency for very heavy load currents. That is why most of the time we are using it in small circuits. So for heavy load currents, it is having very low efficiency. Why is it so? Because if the load current is large, there will be considerable power loss in the series, that is limiting the resistance. So the efficiency also decreases. So it has very low efficiency. Next, what are the uses of LED? What are the uses of LED? LED is used for TV backlighting. So whatever background light we see in TV, so that is due to the LED, light emitting diodes. Then in displays we see LED. So suppose at the signals you see the timer is there. So if you have to see the timer, they use LEDs because they work in the visible region. And also automotives and also in the dimming of lights, there also we use LEDs. Then which materials can be used to produce infrared LED? Infrared means in this particular region, or the wavelengths are above 7000 angstrom unit. Gallium arsenide has an energy band gap of 1.4 electron volt. So whenever we are talking about gallium arsenide, and the band gap is 1.4. If you are taking an ordinary semiconductor like silicon, the band gap is 1.1 electron volt. So when we are doping and we are taking a combination like this, gallium arsenide, the band gap is 1.4 electron volt, and this can be used to produce infrared LED. Now we may use other combinations also to produce different colors. If you want different colors, you can use other combinations also. We can use gallium phosphide also, GAP can be used to get different color light in LED. Now, which process of the electron-hole pair is responsible for emitting of the light? So, which process? So, it is clear, the recombination process. When are we getting the light or the radiation is emitted? Whenever there is a recombination of holes with the electrons. Energy is released in the form of light. So that is what we call as light. So the photon is responsible for emission of light. So the process here we are talking about is the recombination process, which is emitting light in the form of photons. Next, what is the difference between a photodiode and a solar cell? So the solar cell does not need an external bias. So we need not do the biasing for a solar cell. You can use it as it is. It simply works on the incident solar radiation, which causes the creation of electron-hole pairs. So in case of a photodiode, we have to do the biasing. Now we do the forward bias in case of photodiode, means the p-type connected to the positive and n-type connected to the negative. But in case of a solar cell, we don't need any external bias. The light when it falls or the solar radiation when it falls on the cell, the whole electron pairs are generated. So when they are generated means there is combination, recombination. So energy is emitted. Next, what should be the band gap of the semiconductors to be used as solar cell materials? So when we have to use a semiconductor material in a solar cell, what should be the band gap? So the band gap should be close to 1.5 electron volt, and that is ideal for solar cell fabrication if the band gap is of the order of 1.5 electron volt. So they are made up of semiconductors like gallium arsenide and cadmium telluride. So this is what? Gallium arsenide, and this is cadmium telluride. So both of them have band gap around 1.4 electron volt, about 1.44 electron volt to be precise. So these are generally preferred materials in solar cells. Now what happens in a pin diode? Pin diode for low frequency model. So first let us see what a pin diode is. Pin here means there is an intrinsic semiconductor material between P and N junction. So now suppose if you are talking about a PN junction diode, this is P and this is N. So in between we are having an intrinsic material. Intrinsic means which is pure. When I am talking about P-type, it is extrinsic. We are doping it with trivalent impurity. N-type, we are doping it with pentavalent impurity. So these two are extrinsic. But here, in between, if you are having an intrinsic semiconductor material, means which is pure, then we call it as pin diode. So in a low frequency model, the resistance decreases and the reactance increases. So resistance means the obstruction for the flow of current decreases, and the reactance here, it means the impedance due to the components like inductance and capacitance which is there in the circuit, that will increase. And here the variable resistance is neglected. We are going to neglect the resistance because it keeps on decreasing. So at low frequencies, the charge can be removed and the diode can be turned off. So we are what is happening at low frequency? We can remove the charge easily and it can be turned off. So for more definitions and details, you can refer to these books: Engineering Physics by P.K. Palaniswamy, Engineering Physics by Gaurav Gupta, and also Modern Engineering Physics by Vijay Kumar and Chandralingam. So thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.